This is algebra 2, lesson 5.4, complex numbers. We're performing operations with complex numbers, and then we're applying it to fractal geometry, beginning on page 272. Starting off with a handful of definitions. First one is an imaginary unit, or the imaginary unit I. It's defined I is equal to the square root of -1. Again, it's called imaginary for a reason because there's no real number that gives you the square root of a negative number like 1. So I is the square root of that. It allows you to take the negative value out. So it makes it 1I in this case. A complex number is a number A plus BI, where A and B are real numbers and I is the imaginary unit. This is also the standard form of it, which will come up next. But A plus BI, where this one and this one, these are real numbers. Just like the square root of -4, I times the square root of 4, this is a real number, the square root of 4, which is 2. This is the imaginary number. When you start talking about complex numbers, there's just a binomial. There's something plus that. So it'd be like 3 plus the square root of -4. Standard form of a complex number is whatever that number is, whatever that real number that's not multiplying by the negative value under the radical. That goes first. And then the coefficient b times that I value, that negative value. So to form A plus BI, where A and B are real numbers and I is the imaginary unit, that's the same definition as this one here. A plus BI, where A and B are real numbers, I is the imaginary unit. The number A is the real part of the complex number, and BI is the imaginary part of the complex number. So this is the form, this is how you're going to put it, A plus BI, just like that. That's how you're going to put it. Just like you don't put X4, because that looks funny, that's wrong. You put it 4X. With complex numbers, you're going to put whatever the A value is plus B times I. You'll get used to putting in that form. An imaginary number is a complex number where A plus BI, where B can't be 0. Because if you have 0 there, remember, 0 times anything is 0. So what it would do is it would eliminate that, and then you would just have a real number, A. So imaginary numbers, B's value can't be equal to 0. And then a pure imaginary number is something where A's value is 0 and B's value is not. So a pure imaginary number doesn't have the A value. So like 3 plus 4I, this one's not here because this value is 0. It's just like 4I. That's a pure imaginary number. That's the difference between an imaginary number and a pure one. An imaginary number has something here for A, like I said, 3 plus 4I. This is an imaginary number. It's a complex value, 3 plus 4I. This one here doesn't have the 3 value. It's just the 4I part. Okay, a complex plane. Sounds confusing, but this is really all it is. You know how to draw a regular plane. If I told you to plot 2, 3, you would go 1, 2 this way, and you would go 1, 2, 3 this way, and you would put a plot right there. You'd plot a point. That's 2, 3. Okay. With a complex plane, this one here, this x value, this is the real one. This is the real number. And this one here, this y axis, that's the imaginary number. Y is the imaginary number. So A plus BI, if we go back to the same one I said a second ago, 3 plus 4I, this is your real value, and this is your imaginary value. So you would go 1, 2, 3 to the right, and 1, 2, 3, 4 up, and the plot would go right there. This is X, this is Y, 3, 4. Very, very, very simple concept, complex planes. Okay, complex conjugates. This is something we're going to talk a lot more about tomorrow. But it's two complex numbers of the form A plus BI and A minus BI. Last week we talked about if there was a radical at the bottom, what you have to do about it. How do you get rid of the square root of 3? We said we multiply by the square root of 3 over the square root of 3. That's rationalizing the denominator. That's the only way to get rid of that. That gives you 2 times the square root of 3 over 3. All we did right there in that part was rationalize the denominator. The reason we're talking about this word conjugates is because if there is something that is not a monomial at the bottom, so this is what I mean by that. If at the bottom of a fraction, you have something like 3 plus the square root of 4. Notice that that's not talking about complex stuff here. Just 3 plus the square root of 4. Two different, well, let's use something besides 4. 3 plus the square root of 2. Okay. You can't rationalize this by multiplying it by the square root of 2 over the square root of 2. This doesn't do it because it's not just one term. It's not just a monomial. You can't do just this because this bottom term, this denominator, is not just the square root of 2. It's 3 plus the square root of 2. So the way you get rid of this is you use what's called the conjugate. All the conjugate is the same two numbers, 3 and the square root of 2, except it's the opposite of this sign. So instead of being times 3 plus the square root of 2, you multiply it times 3 minus the square root of 2. And just like this one here, you would do the same thing here. So 3 minus the square root of 2 over 3 minus the square root of 2. And that'll help you undo it. So a complex conjugate, if you look at everything that I just told you, a complex conjugate is the same thing. It's A and it's BI. It's A and it's BI. But the difference is one's positive and the other one's negative. So the conjugate is the opposite sign with the same numbers. And again, we'll get more to that when we do division of these complex numbers tomorrow. And then we're not going to do absolute value at all, everybody. So we'll leave absolute value off for this lesson. We'll catch that at a later lesson. The square root of a negative number. Okay, so right here it says if R is a positive real number, then the square root of negative R is I times the square root of R. So it's the imaginary number, I, times the square root of 5 in this case. So you just pull a negative value out, and it makes it the square root of 5. So by this property, it follows that I times the square root of R squared is negative R. So remember, if we have the square root of 2 is equal to x, or if we do it the other way like we had last week, x plus 2, the square root of x plus 2 is equal to 3. Square root of x plus 2 is equal to 3. Last week we said in order to undo the square root of something, you square it. If you square it there, you square it here. Same thing with this. So right here, it says the square root of this. When you square it and you square both sides like this one, it just gives you the negative value. So if it was I times the square root of 5, when you square that, this cancels out this, and you're left with I squared times 5, and I squared, all you have to remember about this is anytime you see I squared, that's the same thing as negative 1. And that's why negative 1 times that becomes negative 5. So when you see that, everybody add this in real quick. I squared is equal to negative 1. Anytime you have I squared, you count that as the number negative 1, and this stuff's easy. Example number 1 says solve this quadratic equation. 2x squared plus 3 is equal to negative 15. Now this is not I squared, so don't put negative 1 in place right there. We're talking about x squared here. You're going to work your order of operations backwards, just like last week. Addition, subtraction, multiplication, divisions, exponents, radicals, parentheses. So undo. 2x squared plus 3 first by subtracting 3 on both sides, here and here. So 2x squared is equal to negative 18. Then it doesn't say 2x squared plus or minus anything anymore. It says 2 times x. So you go multiplication and division. Undo that by dividing by 2 on both sides. Divide by 2, divide by 2. X squared is equal to negative 9. Then you go to the next step, exponents and radicals. Undo x squared by taking the square root. You take the square root on the left, you do the same thing on the right. So right here, now we have something that says x is equal to both positive and negative square root of negative 9. Remember, there is no real solution that when you multiply it by itself gives you a negative value like 9. So in order to take the negative out of that radical, we have to multiply it by I. So notice the only thing that changed from that line to the next line is the negatives outside of the radical, and it's multiplied by I, but it is still plus or minus I times the square root of 9. So we know what the square root of 9 is. It's 3. So we have plus or minus 3I. So the solutions are 3I and negative 3I. And all that is right there is taking this symbol right here and separating it into two separate answers. Positive 3I, negative 3I. So again, order of operations. Only thing we're adding this week, the only thing we're adding today is we're taking a negative value out of the radical. So in the little white space on the side, do this one. 2x squared plus 26 is equal to negative 10. Order of operations backwards. Addition, subtraction, multiplication, division, exponents, radicals, parentheses. Take about 30 seconds. Okay, at the end of this problem, we wanted to say x equals just like everything else we solved. So you want to undo addition and subtraction first. You have plus 26, so take care of that. Do it there, do it here. Negative 10 minus 26, those are the same sign. You add them up and you keep that common sign negative, so negative 36. We still have 2x squared over here, so we're past addition and subtraction. Now we're at multiplication and division. Undo 2 times something by dividing by 2. Do it there, do it here. Negative divided by a positive is a negative. 36 divided by 2 is 18. So now we have x squared is equal to a negative 18. Then undo the next step, exponents and radicals. Undo squaring something by taking the square root of it. You take the square root of the left, take the square root of the right. This cancels out just like the rest of it canceled out. X is equal to both positive and negative square root of negative 18. Remember, you cannot have a radical that is a negative value. There's no real number. So in order to make this complex number, in order to get rid of that radical, all we do is we take this and we multiply. It's still positive and negative, but we multiply it by I. So now we have I times the square root of 18. And then just like on the bell work, we simplify the square root of 18. The perfect factor of 18 is 9 times 2, which is 3 times the square root of 2. Okay, so we're going to take that value and separate this into 3 times the square root of 2. We still have plus or minus I times that. Your standard form of this is A plus BI. A plus BI. Now, there's no A value because 3 is multiplying by I, or I is multiplying by 3. So this is simply 3 times the square root of 2 I. Or if you reorder it, remember, it doesn't matter what order you multiply in. It's actually better to write it as 3I times the square root of 2. And it's both positive and negative 3I times the square root of 2. Example number 2. Example number 2, 1 plus I. Remember, this, anytime you have this value, this is your x-axis, this is your y-axis. There's no value written in front. There's no coefficient for I. So it's 1. So your first plot point is going to be at 1, 1. So 1 unit to the right, 1 unit up. This right here is 1 plus I. Plot that point. The next one, this is x, this is y. So negative 2 is your x, negative 2 is your y. So down, left 2 and down 2. This is it here. Negative 2, negative 2i. The last one, 3, negative 3i. This is x, this is y. To the right 3 and down 3 here. Super duper hard. And we'll get you the rest of this tomorrow.